there was a question about one of the homework that's due today. So this lecture I'm going to go at a slower pace. And there was another question about when the energy equation cannot be used. So this is a good opportunity for you to ask any question. Tuesday of next week, we will continue the lecture on chapter 8. We will be wrapping up. As a matter of fact, we'll be wrapping up the chapter today. But next Tuesday, any loose end of chapter 8 as well as 7, dimensional analysis, we will have some Q&A sessions. And a quick review, don't expect too much. The review maybe like 10 minutes, even 5. And focusing on the new material starting from end of test 1 to now test 2. Then if there's no question asked on next Tuesday, I will start new material, which is chapter 9. All right, and your responsibility for test 2 will be the end of lecture on Tuesday. There will be no more homework assignment than just this set. This is still next Tuesday. All right, so are you clear? And the test will be inclusive, meaning I have to give you problems that include continuity. That's a given. You may or may not include momentum, but you have to prepare for it. So I want to make sure you review all the material starting from the first lecture of the semester, not just from test 1 onward. Is that clear? Any question on the administration of the test? Will be in class 1 week from today. Same format, I'll talk about it. So I will post some practice problem maybe over the weekend. If you want to work ahead, I told you I won't be here the night before to give a study session, but Mike will schedule evening office hour on the Wednesday before the test, so you can have access to him on a one-to-one basis. How's that? So my agenda today is just to touch on the energy equation again. I know it's repetitive, but it's such an important equation, no less important than the momentum and Bernoulli and continuity. I want to make sure you have a good foundation. And then we start a topic that is called minor losses. I will discuss what it meant by that by way of an example. And then the other small section left in chapter 8 is how do you deal with a rectangular duct that you find in heating and ventilation at home, for example. And that's the long circular duct. There will be a quiz, and it involves some calculation. So because of that, I may give that in the middle of the lecture or towards the last 2/3. And so face down, don't cut it off until I tell you to. And both quizzes has been graded, and I'm going to return that back to you. And for whatever time left for today's lecture, I'm going to pause and just go over some of the homework that not necessarily that you may have problem with, but each one of them has some intricate lesson that you can learn as an engineer, and that's what I would like to do. And at that time, you feel free to ask in-depth questions. I hope by the end of lecture today, we clear up all the homework with any questions you have, except for the last set, which is still next Tuesday. All right? Because I'm trying to prime you up and prepare you for the test that is coming. Please don't wait until next Wednesday, 11 o'clock to study at night. All right, other questions before? There are 2 questions outstanding on the homework on the energy equation. I will make sure I address them. So the energy equation, we walk through that in excruciating detail. You can go back and look at the algebra, but more importantly, I want you to be able to step back and look at the big picture and make sure you understand how it comes about. And the question asked was, what, if any, limitation regarding the use of the energy equation? That's a very good question. Can someone help me with that? Again, what, if any, limitation there is, restriction, assumption, when you write down this energy equation? Before I answer that, let me teach you, what are the assumptions involved in the Bernoulli equation? Bernoulli. Ooh, no, not laminar. Bernoulli look like this, except the right-hand side will be equal to what? 0. So what are the assumptions, restrictions must be met before you can use Bernoulli? And I'm going to trick you in the test. I can guarantee you. Yes? Implicit. What does that mean? Implicit. No fiction. So immediately, the energy equation had nothing to do with that. The energy equation had fiction. What are the other 3 for Bernoulli? Constant density. What else? A streamline, meaning cannot have turbulent flow. Turbulent flow has no streamline. Cannot apply Bernoulli through a compressor or turbine because the flow is constantly chopped up by the blade. All right? What is the last assumption? Steady. Steady. If those conditions are met, you use Bernoulli. Why? Because it's simple. It's a closed form equation that has involved what terms? You have to know this because you'll be testing test 2 with new problem you haven't seen before. And just like SP1, you have to ask yourself, can I use Bernoulli and why? So why do you want to use Bernoulli? What are the terms in Bernoulli equation? What can you expect Bernoulli equation to get you? Pressure, very good. Or velocity, that's it. Sometimes height, not very often, but yes, that's it. Can you get your forces? No way, no way. Anytime you bring in momentum, forces has to be involved. So that small subtlety and distinction is what hopefully will prime you as to when you should use Bernoulli. You know, bottom line, if all the 4 conditions are met, you should use Bernoulli. It's the quickest way to get either pressure or velocity. Is that clear? The toolbox is getting bigger and bigger, right? You have continuity. What are the equation that is in your toolbox now? Continuity, in order I want to hear. Continuity, momentum, Bernoulli. Now energy, energy. So a new problem being tossed at you, you're going to have to scratch your head and say, where do I start? You're going to be challenged. All right, you always start with what? Continuity. Okay? And then? And then? Huh? Bernoulli, if you can use it. Beyond that, whether it's energy or momentum, is very much problem dependent. Very much problem dependent. And I can tell you in the general form. But is that clear? Is that logic clear? So now the energy equation, what are the restrictions, if any, to use this equation as shown? And I assume you know all the terms here now. I don't have to. Do you want me to go through that one more time? What is X of F? That's the question you have last time. Do you understand that? And can X of F be negative? It's a violation of second law if that happens, which is a no-no, okay? So what are the assumptions involved in the form of the energy equation as shown in here?
Adiabatic.
No heat transfer, very good, adiabatic. Why? Because this comes about, which is totally separate from Bernoulli. Bernoulli comes from the Euler's equation of motion. This comes from first law for a control volume, where flow in and out, Q, well, I use S just to remind us it's the shaft volume. That's the convention we use. So besides adiabatic, any other assumption? There's one. Only one. Yeah. Very good. Incompressible. And why? You have to look back at the derivation we did last time. Yes.
Are we able to work with the compressible fluid in this course?
No, you will only deal with constant density fluid, even if it's air. Now, there's some exception, having said that, and you have seen that in the homework, like the gas is hot. Right, so it's not ambient. In that case, the density is changing, but fill in between. Unless you were told specifically in the problem statement, assume constant density. Okay? That's it. That's the distinction between energy and Bernoulli. Do you see that? There are 2 different equations. I've spent so much time to try to separate them. I hope you understand. Any other question on the background and the use and the physics involved in this equation? The part that at times may become challenging, and several students ask me at the end of class, is now that you have this so-called specific work from the shaft, which is energy per unit mass, how do I then go about to get, say, a power? That's the part that always, for reason that may be not obvious, you get the power by mass flow rate times the specific work. So sometimes this equation is not well understood and not well used, and the m dot is simply rho VA or rho Q. And that's how we did that pipe problem of 9 miles of gasoline being pumped over a long distance. So that's just a recap. But this is it. This is the last call for any question on the energy equation. Yes?
Q is volumetric flow in that.
Good call. So I actually read the handout on nomenclature, and it is now becoming more and more dangerous, because just like the question asked, I have Q here, I have Q here, I have V, sometimes I have small v, that can be volume, that can be velocity. This Q and that Q have totally different meaning. This Q is what? Volume flow rate. That Q is heat. Okay, so please be alert and be able to separate the nomenclature. Yeah?
I think, if I heard you correctly, you said earlier that the WS in power is specific work?
Okay, so let's time out. Let's time out. Let's yeah, I am very bad here. This nomenclature should be capital WS. This small s is, yes, this is, well, in kilojoule. Heat transfer in kilojoule. In cap. Once I go to a small alphabet, this is, everything in small is specific. Well, which is what unit? Per unit mass. And hence, this is just kilojoule per kilogram multiplied by kilogram per second, which is kilowatt or horsepower. Got it? Yes?
So if you wanted power in terms of H+, would it just be rho Q multiplied by G?
Okay, so how do you relate, how do you get the X sub S to relate to W sub S? Let me answer that by the example we did. And if I fail to answer your question, ask me one more time. Okay? So that is just, I keep repeating it because I think it takes a little time for it to sink. But once it sinks, you are comfortable. So I hope we are close to that now. So this example we watched through at the end of the lecture last time. I want to come back, not go through the mechanic, but just look at the big picture. Step back and say, hey, what did we learn? What happened if you make a mistake in reading the friction factor in the Moody diagram and you buy a pump that is 50% of the power? Okay? So what we did, just to recap the problem, I have a long pipe, a given flow rate, given diameter, from which, from the Moody diagram, I can estimate between the two pumping stations, not including the pump, from 1 to 2. So this energy equation has no shear work, purely frictional losses, right? And from that, I calculate the equivalent head loss due to friction is about 5,600 meter. Meter of what? Meter of gasoline, right? Can you do that? Can you do that? So next step then is, and maybe I should give you a schematic or roadmap, which is something we will use as an anchor. So it's a scheme of solution using the Moody diagram, and it's repetitive. Now that you have seen the example and done some homework, typically I'm given a geometry, just like this gasoline problem. Tell me the length, tell me the diameter. And then you have to tell me how fast you want to pump the flow. An average velocity or Q. Right. From that, just like what we did, I can calculate the Reynolds number. And knowing the build of the pipe from Moody diagram, I get the friction factor. So that step is what we did last time. Any question on that? What's next is from the Moody diagram and the definition of friction factor. I can translate that to a frictional head loss, X of F. And that's how we get this 5,600 meter of equivalent head loss in gasoline. Then I can translate that to pressure loss in PSI or kilopascal, simply, and this is a very important equation you need to remember, simply using OGH. Rho in this case is the fluid in question, which is gasoline, not water, not mercury. Right? So this step sometimes need to be emphasized. Anything given in measurement of height, head, like 760 millimeter of mercury for ambient pressure is equivalent to telling you low GH. Get used to it. So that's now my pressure of little less than 400 atmosphere. And then the energy equation, which is a little tricky, and I watched for that last time, is now that I've estimated the frictional loss from this 9 mile of pumping, the only way I can have energy added to the fluid to overcome this length is to have a pump. This pump is a repeating section of which all the energy lost to the friction must come from the pump. No more, no less. There's no gravitational add, nothing else. So here, the energy equation, concluded is all frictional head loss must come from the pump. Do you see that? This is a little subtle. I'm not applying energy equation from ahead of the pump to behind the pump. So from that, and using the power equation on the left, we get in total $7.6 megawatt. So let's think of a scenario. You misuse the Moody diagram, or you calculate the Reynolds number off by a factor of 10, and your friction factor is considerably lower. You buy a pump, instead of 8 megawatt, you buy a pump, just for the sake of argument, 6 megawatt. Put it all in, you turn the power of the pump, what happened? Can someone tell me what will happen? Nothing moved. Close. Something will move, but it's not enough to overcome all the friction. So to start from the beginning of the 9 mile, somewhere in between 7 miles, 6 miles, the flow will stop. So now that is not a steady flow. It's not steady anymore, because your pump simply don't have enough power to overcome all the friction. So it's a transient problem. You turn the pump, flow will start, and they will die. Yes?
If the pipe was already full of water, would nothing move? Like if
That's a different problem. Yeah, that's a different problem. They will move, but then they will die. They will not have enough power or energy to make it at the end of the 9 mile. Okay, so bottom line is a transient problem. It's no longer steady state. There's just not enough energy to overcome all the friction. So do you see, sometimes you get kind of, the friction is confusing because in the past 2 months we always assumed invisible flow, and that's very easy to understand. Now there's some friction and make the problem a little bit more spicy. So you need to kind of understand continuity, say, oh, what comes in that goes out. Does it mean that even the pump has not enough power, the flow will go out the other end? No, it will stop. And you have a totally different problem. Yes?
Was HF given?
HF what? I'm sorry?
Was the HF in this problem given?
No. No. See, okay, so way back when we do the fire hose problem 2 weeks ago, that HF was told as 7 meters of water.
Right.
for that fire hose problem.
Yeah, we were told that.
You were told that because prior, we have no idea how to estimate that. That was back, say, in chapter 5, the problem you done for your homework. There was P Moody diagram, so I have to tell you how to estimate the friction. You don't know who is Moody yet. Now the problem is completely changed. You are now equipped with a tool. If I give you a full system, meaning the pump, size of the piping, what builds, and how fast I want to pump it, you are capable of using Moody diagram and estimate that 7 meters. And that's what we did here. Yes? Other questions? Do you see how all the pieces fit together? Yes? No? So you're the Exxon engineer who just spent $500 million, B, to buy all that pump and lay out all the plumbing from Anchorage to Seattle. And you're off and it's not working. What are you gonna do? Get fired? Oh, be smart. What can you do to fix it? What can you do to fix it? Anyone? Yeah, you can replace all the pump, that's expensive. What can you do without changing any of the hardware? Anyone? What can you do to attempt to change the friction factor or change the Reynolds number so that you consume less power? You slow it down. You change the cube. You change the cube. All right? So, just food for thought, and I thought that may be of interest in the context of all this energy equation and the Moody diagram. Any question on that? Any question on the shape of the Moody diagram? The linear, inward, laminar, pressure drop, and so forth. Yes?
How would you actually change the flow rate of that in the pipe?
You use the valve, which is the next topic. So how do you adjust the valve? Two-way, yeah. Most inexpensive pump use a constant speed motor, so you cannot change that. But what you can change the flow rate is you use a